In this module, we're going to look into how to sketch the graph of a function. In the previous module, we have seen how to find the intervals of increase and decrease and the local extrema of a function. Now we're going to look at further qualities of the graph of the function that we need to clarify. So here is a curve, and we want to look at what's important about this curve. So let's imagine for a second that this is a road seen from above and that you're driving on it. See that on this portion of the curve you would have to turn right all along until around this place where you would have to start turning the other way and turn left. So as you can see, it is important for us to find this point where instead of turning right, we start turning left. So it's a point where there is an important change in the shape of the curve. And this is something we need to be able to find. Similarly, we need to know on what portion of the curve we have a shape that corresponds to turning right or to turning left. So let's try to clarify this. Let's say I know that the function is increasing on the interval AB, so it goes between these 2 points. That doesn't tell me whether it joins these 2 points in an increasing fashion this way or that way. And as you can tell, this looks quite different. So what makes a difference in terms of shape? Of course, we talked about the kind of difference it would be if you were driving on that road. But let's try to see another way to look at it. Let's look at the red one, the one where I would have to turn right. You see that the tangent lines have a slope that is decreasing as I move from left to right. So the tangent lines to the graph have decreasing slope. In other words, f prime of x is a decreasing function because f prime gives me the slope of the tangent line. But we have seen in the previous module that a function is decreasing when its derivative is negative. That is, of course, assuming that the derivative exists. So if f prime is differentiable, in other words, if f has a second derivative, then we have this kind of behavior if the second derivative is negative, because that means the first derivative is decreasing. In other words, the slope of the tangent lines are decreasing. On the other hand, if we look at the other kind of shape, the kind of shape where I would have to turn left if I was driving on the road, then you see that the slopes of the tangent line are increasing. So that means that the function f prime is increasing. In other words, its derivative is positive, and that is the second derivative of f. So that brings us to this definition. We're going to say that a function is concave up, and that corresponds to the blue shape, concave up on a certain interval if f prime is increasing on that interval, and that it's concave down on a certain interval if f prime is decreasing on that interval. As we have seen, provided that the second derivative exists, that means that concave up means that the second derivative is positive on the interval, while concave down means that the second derivative is negative on the interval. And now, a place where we have a change of concavity, in other words, the shape changed from concave up to concave down or the other way around, is going to be called an inflection point. That is the case provided that this is really a point on the graph of the function where we have a change of concavity. Another kind of situation where we may have a change of concavity, as we will see later on examples, is on vertical asymptotes, for instance. But in that case, it may not correspond to a point on the graph, and in that case we don't have an inflection point. So again, an inflection point is a point on the graph of the function where the concavity changes. So let's look at an example that we have already looked at in the previous module. It was the function x cubed minus 12x plus 1, and we've already looked for the intervals of increase and decrease and local extrema. Recall that here the derivative is 3x squared minus 12, so we can factor it. Factor out 3 first, second factor is x squared minus 4, which factors further as x minus 2x plus 2. So that leads us to this sign table for the sign of x minus 2 and x plus 2. And as we have seen before, that gives us that f prime is positive on the interval negative infinity, negative 2, and on the interval 2 infinity, and negative between negative 2 and 2. For the intervals of increase and decrease, we obtain that f is increasing from negative infinity to negative 2 and 2 to infinity, and decreasing between negative 2 and 2. Okay, as we have discussed, that tells us only whether the function is increasing or decreasing, but not the type of concavity of the graph. We have seen that the concavity depends on the second derivative, on the sign of the second derivative. So we calculate the second derivative, and in that case, it is simply 6x. So the sign of the second derivative is the same as the sign of x. In other words, the second derivative is going to change sign at 0 and be positive whenever x is positive, that is on the right of 0, and negative when x is negative. The interpretation in terms of concavity is that from negative infinity to 0, the curve is concave down, because the second derivative is negative, and from 0 to infinity, the curve is concave up, because the second derivative is positive. So now, we have a change of concavity at x equals 0, which corresponds to a point on the graph. We can plug x equals 0 in the function, and we obtain the point of coordinate 0, 1. This is an inflection point. And this is the only inflection point because we only have this place where we have a change of concavity. Of course, you see here that from the first derivative test, we get local maximum at negative 2, and to get the y coordinate of this local maximum, we just plug negative 2 in the function and get 17, and we have a local minimum at 2. To get the second coordinate, we plug 2 in the function and get negative 15. Plugging all these important points, the local extrema and inflection points, in my table, I have 17 at negative 2, 1 at 0, and negative 15 at 2. So now we are in a position to sketch the graph of the function. More explicitly, if you want to sketch the graph of the function from the information we have gathered in this table, first you start by plotting local extrema and inflection points, and also asymptotes if any, but here we have a polynomial function, so there's no asymptote. So we have a local maximum of coordinate negative 2, 17, a local minimum of coordinate 2, negative 15, and at both these places the derivative is 0 and we have an horizontal tangent. Additionally, the next important point is this inflection point of coordinates 0, 1. Then we look at the table and all the intervals that we have between the important points. So here we have on the interval negative infinity, negative 2, we see that the function is increasing and concave down. Okay, so we have a function increasing concave down until we reach the local maximum at x equals negative 2. Then between negative 2 and 0, the function is still concave down, but now decreasing until we reach the inflection point. So concave down, decreasing. When we reach the inflection point, we have a change of concavity, and from 0 to 2, you see that the function is still decreasing, but now concave up. So this is what we get. This is until we reach the local minimum with an horizontal tangent. And then from 2 to infinity, the function is increasing and concave up. So it looks like that. So now you can turn to the next video to look into another type of information that we can get from the second derivative, namely the second derivative test, which, as the name suggests, is an alternative to the first derivative test to decide if a critical point is a local maximum or a local minimum.